Hello and welcome to today's webinar. Our special guest speaker, Mr. Mark Camps from the Farmhispania Group, is a chemical engineer with a master's degree in production engineering and organization. He has been part of the Farmhispania Group since 2014 and currently works as a process engineer. Starting as an R&D technician on a biotechnology development project, he later contributed to the creation, development, and expansion of the modeling and simulation team, which collaborates across multiple departments. Today, his role involves evaluating processes from various perspectives for existing and active products, assessing new processes during scale-up from the development stage, and analyzing potential projects in their early phases. In this presentation, Mark will explore the various approaches that have been developed for mixing studies, which have evolved alongside a growing understanding of mixing phenomena. We will walk through a standard workflow and illustrate a typical scale-up process from laboratory experiments to full-scale industrial production. Finally, we'll share several recent case studies demonstrating how mixing assessments have enabled the Farmhispania Group to better understand the impact of mixing on multiple unit operations and to optimize industrial facilities to meet the specific requirements of diverse processes. Feel free to ask any questions in the chat box during the webinar. We'll do our best to address them either during the session or via email afterwards. Enjoy today's presentation, and without any further ado, I'll hand the microphone over to Mark. Enjoy.
Hello, everyone. Thanks for the introduction. I hope everyone is hearing me well and seeing the presentation as well. I'm pointing with a laser pointer to the presentation, so I hope everyone is able to see it. Can anyone, Moshe or Marcy, can you please check everything is okay so I can start?
Yes, I can see your screen and I can hear you very well. Thank you,
okay.
Mark.
So let's go. Okay, so the presentation, as the introduction stated, the title is Mixing Assessment, Workflow, and Case Studies. And I will be presenting, let me show you all the content. This is a little bit what I will be explaining today. I will start with an overview of Farmhispania Group, who we are and what we do. I will continue by explaining a little bit what we do when it comes to mixing assessment. To give you a little bit of a spoiler here, I will talk about scale-up studies going from the development stage to plant. I will talk about troubleshooting at industrial scale with 3 case studies that I will present as well. And I will show a little bit our usual workflow, which will go back here and talk mainly about scale-up cases going from development to plant. And then I will explain a first case study, which is an actual case study, but would be the idea with it would be to explain what is for us a standard scale-up case, which means everything goes well, the first run with no issues and no troubleshooting needed, and what would be for us our standard. And then I will present 3 case studies. This I show here: case study 2, case study 3, and case study 4. The first one will be all of them are about troubleshooting or optimization and optimization at industrial stage, but the 3 cases are quite different, the one from the other. And the first one will be about a change that we had to do in the addition position for an addition reaction at industrial scale. This was an optimization case. Then we also have a case in which we have to do scale down experiments and with the aid of VisiMix modeling to determine the emulsification risk. I will explain about this case later. And the last one will be a case study in which we had to do industrial modification of an impeller to improve the efficiency of mixing in that particular reactor. And I will, of course, close with some final remarks. So firstly, I will introduce a little bit about our company. We are based in Spain. We have 2 sites, one in Barcelona, which is Farmhispania, and the other in Zaragoza, which is Rolabo. Both sites form Farmhispania Group. although the two companies have separate names. And we are a private company that in 2023, the revenue was a little bit higher, a little bit above 150 million euros. We are 700 plus employees with 80 plus scientists, and we produce a combination of more than 50 APIs and highly potent APIs. And we have to separate, as I state here, two separate lines of business. One is for the production of generic APIs, and the other is we are a CDMO company, so we produce products for our customers. We put the facilities and they put the process, so we can produce for them. Regarding Farmhispania, as I said, we are located here in Barcelona. We have several different facilities. We have a special plant, which is a high potency compounds plant with capacities for OEBs up to 5. I mean, up to OEB 5. This is a separated and specially dedicated area with a cascade, with a triple pressure cascade system. And we have reactors ranging from 10 liters to 1600 liters. We also have industrial preparative chromatography here in this special area. And then apart from the HP API area, we have a kilo lab and a pilot plant for up to OEB4 with reactors ranging from 60 to 1600 liters. And of course, a large manufacturing area with reactors up to 8,000 liters. We have here actually 4 different plants or buildings which are multi-purpose. And here we have industrial lyophilization expertise as well. And of course, different types of solid liquid separation systems and filtration and centrifugation, and of course, drying as well. When it comes to Rolabo is located in Zaragoza, as I said before. We have here a fermentation plant up to OEB5 as well. We have reactors ranging from, or fermenters ranging from 10 liters up to 16,000 liters. We have a filter press and tangential flow filtration technology. We also have here a kilo lab and pilot plant, as I said, in Farmhispania. And of course, a large scale manufacturing plant. Here we have as well 4 different multi-purpose buildings. And we have, apart from reactors up to 8,000 liters, as in Farmhispania, we have here as well hydrogenation, cryogenics, and we have a large-scale multi-purpose GMP flow chemistry kit, which is one of the latest technology we acquired in the company. And that would be more or less an overview of our company and our 2 sites. And now let's jump to the presentation itself. As I said in the introduction, I want to talk a little bit about the 2 scopes or the 2 different approaches that we apply to mixing. When it comes to analyzing or assessing mixing, we can do it in 2 separate aspects. The one is when we evaluate processes that are being scaled up from the process development scale. Here you can see a laboratory reactor, a pilot scale reactor, and an industrial reactor. And we usually assess mixing since the early stage of development. We usually do lab scale experiments, which are designed taking into account the pilot or industrial facilities. And after the pilot scaling, we usually use the conclusions we draw from there, and we implement it if possible before scaling up to the production stage. The following presentation is about or better said, the following slide is about the usual workflow that we apply to these cases, which are all of the studies that we do when it comes from development stage. And the other type of mixing assessment that we do are the studies related to troubleshooting or optimization from pilot scale or industrial scale. In this case, we usually try to do mixing assessment for processes that are that we see or where we identify a problem, or instead of that, to processes we feel there's room for optimization. In these cases, we usually do modeling for the industrial process, and we assess the mixing. And sometimes we can end up with the conclusion that mixing is not really affecting these problems we see, or we cannot optimize the process from changing mixing. But in some other cases, this mixing assessment can lead us to doing scale down to laboratory experiments and rescaling up afterwards, or in some cases we can even do it can even lead us to industrial facility optimization, changing impeller or changing conditions, as we will see in the case studies that I will present afterwards. Now, as I said, as I promised, I'm going to show a little bit our usual workflow. This is what is, let's say, our protocol. It doesn't mean that we always do all the steps in here, but that would be our ideal workflow when it comes to mixing assessment from the development stage. So we usually start in the laboratory. Our colleagues, process chemists, do the first familiarization experiments at lab scale. This can be in small scale reactors from, let's say, 100 milliliters to probably up to 2-liter reactors. And then we do the lab scale modeling, so we can understand better the process. We analyze the mixing parameters. We try to understand which parameters correlate to different results to the process. So we basically try to identify if there are any mixing sensitive parameters in the process. Then at this stage, when we know which will be the scale-up reactor, whether if it is a pilot or industrial reactor, we try to do the industrial scale modeling in this early phase. Sometimes when we are at this early phase, we don't know yet which will be the industrial reactor, but we have typically, for example, 2 or 3 candidates, depending on the scale that we're planning to scale up to. So we can do the modeling for the different reactors which are candidates for scaling afterwards. Then we compare the mixing parameters that we have identified as the most important for the process, and we see if the results are matching. If the results match, meaning that what we have done in the lab scale experiments can be reproduced at the industrial scale, then we usually do a lab scale demo batch or demo batch modeling, and we do a demo batch lab scale experiment as a confirmation. As I said here, the first experiments are typically performed with reactors ranging from 100 milliliters to up to 2 liters. And then here, the demo batch experiments are usually 5 liters or 10 liters laboratory reactors. In the case that the results don't match here, which happens sometimes because laboratory reactors are not always prepared to reproduce the same behavior as in industrial scale, then we do further lab scale experiments. And these lab scale experiments are usually designed based on the in silico results, meaning that we work together with our colleagues in the laboratory, with the R&D team and the process chemists to try to design the configuration of the agitation system, agitation speed, a baffling system, type of reactor, and so on. So we can design something that can be easily reproduced when we scale up to pilot or industrial scale. Then we do, as I said, after this, the lab scale demo batch. After some modeling, we do the actual demo batch. And we try to analyze if the demo batch is successful. At this stage, we've been assessing mixing since 2020, more or less. And although not all the process have been assessed, because sometimes we don't have the resources to do so, I think that we haven't found any demo batch which was not successful at this point. If we had found a demo batch which was not successful at this point, we should our protocol would say that we should have to go back to further lab scale experiments and reevaluate, and sometimes maybe we think we could even reach the conclusion that mixing is not that important and there's something else affecting the process. But as I said, at this point, demo batch are usually successful almost all of the times. So from there, as we have already done the industrial scale modeling here at the early stage, we can scale up and we design or select the industrial scale up conditions based on what we have evaluated before. So this is more or less our usual workflow. This is what we try to apply on a regular basis for projects coming from the development stage. So I want to show you case study, a first case study, which is basically here. I will not present mixing parameters. I will just want to show you or try to explain what we usually do when we apply our protocol here. So this is a case study. This is a real case study. I won't be showing any data because I don't think it's relevant here. But in this case study, the initial experiments were performed in a 2-liter reactor. As we can see here, it was a wide and short reactor. Actually, you can see here that the diameter of the vessel was even bigger or larger than the height of the reactor. And the type of impeller was a 3-bladed impeller with curved blades, as you can see here, and which has, of course, a radial flow pattern. Here you can see some screenshots from the VisiMix model. And the scale up of this process was going to be in this pilot scale up reactor, which is a 60-liter reactor, which has nothing to do with what we had for the 2-liter reactor here. Here the scale up reactor was a 60-liter reactor with 3 baffles, a deep pipe, and also a lower impeller, which is sort of an anchor, and an upper impeller, which is sort of a pitch blade impeller with 2 blades. So and furthermore, the vessel itself had nothing to do with the laboratory vessel, because it was much narrower with a smaller diameter and bigger in height. So instead of scaling up directly to this, from this to this, what we did first, as I explained before, we had to do a demo batch in a similar reactor. So we planned to use this laboratory 5-liter reactor, which is much more narrower and higher, more similar to the geometry of the industrial, or pilot reactor. And we use this sort of anchor-like impeller, and even though you can see it here in the image, we installed afterwards also a baffling device to do something that is much more similar to what we have in the pilot plant reactor. So we created all the models with VisiMix. We assessed the flow patterns, the mixing parameters for the demo batch. Everything was, I would say, similar to the conditions that we could achieve to the pilot plant reactors, and not very different to the mixing conditions that we had in the 2-liter reactor earlier. So we scaled up, and this is a CDMO case. So we produced for a company, and the customer wanted a first engineering run with just half the reactor filled. And then afterwards, we validated the process with the 60-liter nominal volume of the reactor. And everything went well. All the mixing parameters were aligned, meaning that we could achieve similar mixing conditions by adjusting the agitation rate at each scale, and the scale up was successful. So that's like our standard, our goal, and what we try to achieve when we do mixing assessment, although we don't find any problem, but we sort of collaborate from the beginning with the process chemists, and we try to understand how we can improve the agitation to reproduce the behavior that we've had in the previous stages, and we try to understand if we can do something better in the scale up when scaling up. So that would be the first case study I wanted to show you. And then I will present 3 different case studies, as I said before, that are troubleshooting or optimization from processes that were already at the industrial stage. This first case study that I want to present is from a process which was produced, or a product which was produced in both sites, Farmhispania and Rolabo. we realized that this was something that was known. There was an impurity level which was higher in Farmhispania compared to Rolabo, and this meant that we had to do a purification step, an extra purification step in Farmhispania that was not required in Rolabo, and the purification step meant that the yield dropped about 5 to 10%, depending on the batches, but let's say about 7.5% lower yield in Farmhispania compared to Rolabo. So we tried to assess mixing because this impurity was produced in an addition reaction, meaning that we were adding one of the reagents in a solution to the other reagent which is already in the vessel. We analyzed the differences between the two reactors. The Rolabo reactor was a 4,000-liter glass-lined reactor, and the Farmhispania reactor was, well, I mean, it is because it is still working, a 4,000-liter as well, a 4,000-liter reactor as well, and it is a glass-lined reactor as well. The main differences came when we compared the agitation system. In Rolabo, as you can see here, the agitation system was a 4 curved blades agitator with a little larger impeller, and it was fully radial. And the impeller from the Farmhispania reactor was an impeller with 3 pitched flat blades, a little smaller compared to the agitator in Rolabo, and the flow was axial, because you can see that pitched blades here are quite different from the flat blade or radial blades here in the reactor from Rolabo. So what we did here, we modeled both scenarios, the addition reaction in Rolabo and in Farmhispania, and we calculated some parameters. Here I can show you what we felt like the most important parameters were for this evaluation, and we saw that the energy dissipation, this is the average value, was at the agitation speed that we applied for the batches, 40% lower in Farmhispania, and the mean period of circulation, which is a process parameter, some of you may already know that, but I will explain anyway, related to how well the solution that is being added to the reactor is incorporated to the bulk itself. So this is a parameter which is measured in seconds, was a little bit higher, about 34% higher in Farmhispania. Both parameters we analyzed represented that mixing was worse, let's say, in Farmhispania. But also, we analyzed the flow patterns, and the addition point was the same for both reactors. We added close to the wall, but the flow pattern was a little bit slightly different in Farmhispania compared to Rolabo due to the type of impeller. As I said, this is an axial impeller, and this is a radial impeller. So, as you can see here, the lines from the flow pattern are not as stressed as here. What we did here in this case, after analyzing mixing conditions and the difference between the two reactors, we proposed and applied some modifications to the reactor in Farmhispania. Firstly, we were agitating at 100 RPMs in Farmhispania, but that was the limit from the actual limit from that reactor. So we asked the engineering team to do some modifications to the equipment so we could go from 100 to 120 after doing the calculations, because we estimated that 120 RPMs would lead to a similar energy dissipation average in Farmhispania compared to what we had in Rolabo, even though the mean period of circulation was still a bit higher compared to what we had in Rolabo, but the number, as you can see, could decrease by applying 20 RPMs more than we were doing before. The second modification that we asked the engineering and maintenance team was to include an addition element inside the reactor, so we could add the mixture or the solution not close to the wall, but rather more centered, so it could go directly to the vortex and be incorporated faster. After these two modifications, after these two implementations, we went from 100% of the batches requiring the extra purification in the Farmhispania process to only about 18% in the following year. And we can say that we reduced the purity level about 50%. And as we reduced the impurity level, meaning that we didn't have to perform the extra purification in the Farmhispania process, we evaluated the yield, and the overall yield for this process increased about an 8%. It would be a 12% if we only count on the batches that didn't require an extra purification. So that was quite an improvement, and it all came because our colleagues in the production department asked us if we could evaluate the mixing of the process, and we realized that some modifications could be applied, so we could improve the process a little bit. So that's the first case study. Let's go to the second, which is this one. This is a process in which we started from a fermentation process. We filtered, or we separated the biomass, and in this particular process, the product is inside the cells, inside the microorganism. So we had to make an extraction process. So after separating the broth from fermentation, here you can see the aspect of the broth. What we did here is, in this process, is we have to add a solvent or a solvent mixture so we can extract the product to the organic phase and dispose the biomass without any more product by filtration. We identified, or better said, my colleagues in the R&D department identified that there was a risk of an emulsion here because the mixing conditions with the addition of the solvent provoked that the biomass was breaking, as we could see, and there was sort of an emulsion, and it resulted in a poor phase separation and biomass loss, so we couldn't really separate phases and recover the product. So it was very risky, and we were planning to scale up to a pilot scale, and we decided to stop it and do some assessment before we risked a whole industrial or pilot batch. So what we did here, I asked my colleagues in the R&D laboratory if they could repeat the extraction process, but instead of just agitating, I asked them if they could do some steps and continuously increasing the agitation speed. As you can see here, the behavior of the mixture is quite different as you increase the agitation speed. And even with a 10-liter reactor, here the volume is about 5 liters. You can see that at a very low agitation speed for that kind of reactor, for that scale of reactor, which is about 100 RPMs, you can see that here the aspect of the biomass changes completely from what we have in the beginning, and we kind of observed that the emulsion was appearing here, and there was not complete emulsion, but the phases were difficult to separate afterwards. So what we had done here so far was we were doing the extraction with this kind of impeller in a 10-liter reactor with axial impellers, and the industrial tank that we would use for the scale-up had a Ruston turbine as a lower impeller, which was actually the only one which was covered with liquid, as you can see here in the VisiMix model. So I suggested my colleagues in the laboratory to do the same experiment, the extraction, and repeat it with a fermenter, which had a Ruston impeller, to see what happened with this kind of impeller. Here the images are not as clear as in the other images showed you, but we did the same. In this case, as you may see here in the images, the behavior was quite different. So my colleagues could apply some steps. They agitated at 60, then stopped. They agitated at 80, then stopped. They agitated at 100 and continued, and so on. So they wanted to see if there was sort of a limit in agitation that could be correlated to mixing parameters that would give us a bad result or an emulsion that we couldn't separate afterwards. And they could reach 450 RPMs here without having a complete emulsion, which was promising. So after this experiment, We analyzed all the experiments with VisiMix, with the models, with the help of the models, and we determined that energy dissipation and especially shear rate were the most important parameters here. We calculated the agitation rate we had to apply in the pilot and industrial tanks to perform the extraction with the more similar conditions possible compared to what we had at the laboratory. And we realized that we needed to go to a very low agitation rate. So here we had to ask our colleagues in the engineering department to change the industrial tank so we could agitate at a lower speed that was compared to what was the limit or the lower agitation speed that this tank could achieve. With that lower agitation rate at the industrial scale, we also proposed that we should extend a little bit the extraction time when we went to the industrial scale. And we included also in the batch record the possibility to add an additional extraction step if the yield was not high enough after the 3 initial extraction steps at this stage. We performed a pilot batch with a 1,000 liter reactor, which is exactly the same with the same agitator types as I showed you before in the 8,000 liter reactors, which presented no emulsion. So we could reach good extraction conditions. We could recover the process, the product, I mean. And after that, we went to industrial batch, which was successful as well. So it required a little bit of the modification in the industrial equipment, but we successfully scaled up process. For which we had some doubts regarding the risk of the emulsion. And here I will show you a couple of videos that my colleagues provided to me from the experiments in the laboratory to show you a little bit about the importance of agitation. This is quite obvious, but I wanted to show what it looks like when you compare the fermentation extraction or the post-fermentation extraction at 100 RPMs compared to 1000 RPM, and you can see here how it looks like. The first one, and then the second one, and you can clearly see here that the behavior is completely different, and it's very visual, and you can see it quite easily, without even requiring any mixing assessment, very thorough. But mixing assessment, as I said here, was key to understand how the mixing parameters correlated to the extraction itself and to scale up successfully. So this is the second case study that I wanted to present. And let's jump to the third and final one. And here I will show you a process scale up, which went from 60 liter reactor to 2000 or 500 liter reactor. And we realized here when we performed the industrial batch that there was a higher amount of an impurity compared to what we expected. Here you can see an image, because here there is a distillation, and at the final point the mixture is very thick and the volume is very low. And we thought that the mixing could be a possible root cause for this higher amount of impurity, because even in the actual industrial reactor, we could see here that the agitator was moving, but the mixture was so thick that there was not really any kind of mixing itself, let's say. So here we realized that the ratio between the agitator diameter and the tank diameter was much lower than what we had in the previous pilot batch. So we decided to model this process and see what we could get from there. Here you can see the model for the pilot reactor, which had an impeller for a 60 liter diameter. We had an impeller of 350 millimeters. And for an industrial 2,500 liter reactor, we had a diameter of the impeller which was basically the same, let's say. So here, when we modeled this process, we realized that at the end of this is the start of the distillation. We realized that this process was being performed under laminar conditions, and the energy, as you may see here in the table, was much lower compared to what we had in the industrial, in the pilot batch, which was successful. And as you can see here, the index of uniformity was around 1, or about 1 for the pilot batch, and much lower for the industrial reactor. So here we proposed to replace the agitator in the 2,500 liter reactors. And after evaluating several designs, the final decision was this kind of impeller, which is an anchor-like impeller in the lower side, and a hydrofoil as an upper impeller. And what we did afterwards was we modeled this new impeller with a larger impeller diameter, and we compared the mixing parameters to what we had with the same vessel, but the old impeller, and what we have had previously in the pilot batch. Here, with the design of the new impeller, we could reach power average values closer to what we had in the pilot batch, and as well, if you compare the index of uniformity, it is much closer to 1 compared to what we had in the pilot batch, and much higher, more than double that what we had in the industrial batch that went wrong, let's say. So, but before spending a lot of money and time and changing the industrial impeller, we considered that some scale down tests should be performed before doing the engineering tasks. So we modeled a process or a configuration for a 5-liter reactor from the laboratory. We collaborated with our colleagues in the laboratory with a process chemist, and we designed this reactor with an agitator. We selected an agitator which was closer in the ratio between agitator diameter and tank diameter compared to what we would eventually have in the industrial design that we have proposed. And we comparing these numbers, we saw that numbers were closer to what we had in the pilot. The best thing that we could achieve was not as close to the pilot batch compared to what we could reach with the new design, but we decided to do the scale down as well like this, because we thought that could be successful. And the scale down was successful. So this process has not been rescaled up yet, because it takes time to change an impeller at an industrial scale, as you all may know. But the process was successful. So we will change the reactor as we have just explained, and we will rescale up with a new design. And that's the last case study that I wanted to present. So let me just do some final remarks as a sort of a conclusion to this presentation. I want to share some bullet points of what I think of what we think mixing can give to your better performances, and what you can learn from mixing assessment. So let's go directly to it. First, understanding chemistry is key to understand mixing effects. So we as chemical engineers or process engineers, we are evaluating chemical processes, but we are not the ones who have to fully understand the chemistry. We understand the basic chemistry, but that's precisely what makes us want to work together with process chemists. They understand one part of the process, and we understand the mixing part of the process, so working together leads to better results. Second, knowledge about mixing, I'd rather say knowledge about how mixing affects the process is important for scale up, as I said, troubleshooting and optimization. I have presented a scale up case, troubleshooting case, and optimization case, so you can see that understanding whether it is from the early phases of development or directly at the industrial scale, understanding the mixing through mixing parameters and so on makes you understand better the process, and is key to being able to scale up or understand or optimize industrial scale processes. We try to be consistent with geometry within the possibilities, meaning that we try to reproduce at laboratory scale what we have in the industrial scale and not the opposite. I mean, we do not go to industrial reactors based on what we have done previously in the laboratory, but what we actually do is that we assess the industrial reactors in advance so we can change the configuration in the laboratory reactors before we scale up, so we can match the results as close as possible. The fourth point here is evaluate mixing through mixing parameters and dedicated experimental work. As I said, we work together very closely with process chemists, which are the people who actually are running the experiments. And we try to evaluate the mixing parameters, compare them from one scale to the other or one reactor to the other, and we try to design, which is the last point, the mixing experiments based on previous knowledge. So that's the closing final remark that I have here to show with you all. And I think that has covered everything I wanted to explain. So I'm done. If there are any questions, I will be more than happy to try and ask them.
Yes, first of all, thank you so much, Mark, for that wonderful presentation, very informative and very, very interesting. And yes, we do have some questions in the chat. So I'm going to start with the first one from Ara. He or she is talking about the L/D dimension of, does the L/D dimension of the reactor also play an important role in the first case study?
Yes, in the first case study, as I said, it is the typical case study in which everything goes well. So we didn't really have to go very thorough or very deeply into the mixing knowledge there. We basically realized that everything, I mean, in every scale, we could reproduce similar mixing parameters. So we just scaled up based on that. We tried to match the L/D ratio because even though mixing parameters could be achieved or even though we could achieve similar mixing parameters, we thought that the flow pattern could be different, and that's what we realized through the VisiMix models that we obtained. So we decided not only to match the mixing parameters themselves, but the flow pattern as well. So in this case, perhaps it was not that important, but we tried to, as I said in the last presentation, we tried to be consistent with the geometry of the different scales and reactors. I hope that answers the question.
Thank you. Okay, so we have a couple more, or a few more actually. So another question that came up was, hi Mark, I always wonder about what is the meaning of the energy dissipation difference actually?
Moshe, do you want to explain it? As you are.
I think Moshe is not here right now.
Okay. So yeah. Could you repeat the question again? I will try to answer.
So, hi Mark, I always wonder about what is the meaning of the energy dissipation, and if there's a difference actually.
I don't really understand the question because he's asking what is the difference between energy dissipation and what. So we're trying to compare energy dissipation with some other. I can answer. Yeah, go ahead.
Go ahead. Please. Go ahead.
No, please.
It's basically, this is the question, and maybe if the person who is asked it can elaborate a little bit more about this.
I can answer
clarify.
I can answer what energy dissipation is, but it seems like the question tries to compare it with some other parameters, and I don't really know which one they want to compare it to. So energy dissipation is the ratio. The units for that are watts for unit per unit kilo, and it is the ratio at which kinetic energy transfers from the impeller to the liquid. as thermal energy. So kinetic energy changes towards or flows towards maybe flow is not the word the most appropriate word, but flows towards changes towards thermal energy, and the energy dissipation is a measure of how fast this happens. It basically measures the intensity of the mixture. I hope that answers the question. If a person in the audience can elaborate more, I will try to elaborate more my answer as well.
Okay, thank you so much. We have another question. Sandeep is asking, in the case study number 1, why half the volume and full volume studied in CFD?
Why was not studied in CFD? You mean?
So he's saying that in your first case study, why was only half the volume and full volume studied in CFD? So my understanding of this question, I hope I understand the question correctly. He's asking why I may be using when you were working with VisiMix, you were working only with half the volume, and then if you were working with CFD, you were studied on the full volume. You made some simulations on the full volume. I think that's my understanding of the question.
I don't really understand the question, so to be honest,
okay.
I won't answer.
Okay.
Maybe it has something to do with this slide I am showing now, which in case I didn't explain myself well, what we did here was the customer first asked to do an engineering batch with just half the volume. So we modeled the conditions for 30 liters, and we applied the usual workflow, and we calculated the agitation rate as to perform this first engineering run with just 30 liters, which was successful. And then after that, applying the knowledge that we have gathered from this first experiment, we went to the full volume, which was the validation actual volume that the customer wanted to go to. So that's what we did. I hope this gives a bit more of insight regarding this slide. And if you want to elaborate more about the question, I could possibly answer it. If not,
okay, very good. Okay, so we have time for a few more questions. So another question that came up is, for liquid anti-solvent crystallization, what is to be controlled during scale from lab reactor to plant reactor? For instance, like a P/V ratio, tip speed, or etc.
Yeah, this is a very usual process that we evaluate anti-solvent addition crystallization. We usually look for mean period of circulation, which is actually what I showed here. Let me go back a few slides. Here. This is not a anti-solvent addition crystallization. This is an addition reaction, but this parameter, mean period of circulation, apart from energy, which is something that we usually generally evaluate for all of our processes. As I said before, mean period of circulation is a measure. Let me simplify the explanation, but it is a measure of how well the liquid that we are adding incorporates and mixes and fully homogenizes with the bulk that is already there in the reactor, in the vessel. So the smaller this number is, the better for the addition. As we are talking about addition, we can control another different parameter, which is the addition rate. Not only the mean period of circulation is a mixing parameter that can change if we change the configuration of the reactor, or if we change the agitation rate. But the other thing that we can adjust is the addition rate itself. So when we evaluate anti-solvent addition, we usually calculate a coefficient, which is the ratio between the addition time divided by the mean period of circulation. And we try to match this parameter. When we scale up, we may find that the industrial reactor or the pilot reactor is not able to reach a similar mean period of circulation with a similar energy dissipation, meaning that perhaps we can match mean period of circulation, but increasing the agitation speed, so the energy dissipation increases a lot. So when that's the case, we try to match energy dissipation or not go that high in energy dissipation. And even though the mean period of circulation is different, we try to adjust the addition time, so we can make the coefficient between addition time and mean period of circulation the same or the closest possible. So that would be the parameter we focus the most for those type of studies.
Okay, thank you. So there was a clarification regarding the energy dissipation question. So the gentleman said, I mean, how can I understand if there is a difference of energy dissipation? So does that clarify a little bit more?
Yeah, I think I understand the question now. That's something that I suffered. I had to deal a lot with when I started 5 years ago, understanding or assessing mixing. I think he means how to evaluate if a different number means a significant difference in energy dissipation. If that, I hope that's the case. I hope that's what he's asking. That's something I struggled a lot at the beginning, and then after several case studies, we learned to try to understand the impact of the mixing parameters from the beginning. I mean, when we do, as I said here, when we do the first laboratory experiments here, when we apply our usual workflow, we usually try to not only find the mixing conditions that lead to good results, we usually try, or our desire is to find mixing conditions that lead to bad process results. So we can, through the VisiMix models, we can calculate the mixing parameters, and we can correlate the mixing conditions or the mixing parameters to good or bad process results. Sometimes it's not bad process results, but worse process results, or slower reaction rate time, or slower reaction, or higher impurities, or whatever. But we try to correlate mixing parameters to good or bad or worse or better results, so we can understand while scaling up which impact will these mixing parameters have on the process when we scale up to the industrial scale. And we try to adjust what we do in the industrial scale based on the results that we've had in the previous experiments. I hope that really answers the question.
Okay, great, thank you. And I think we have time for one more question. So another question that came up here was, how do you choose the key parameters to be evaluated in VisiMix for different processes? Thanks.
That's a very good question. Actually, there's a guide or a guidance document, a guidance PDF that VisiMix provides that explains and correlates, and Dr. Moshe Ventolila can elaborate more with their customers when we met for the first time, and we asked a lot of questions at the beginning. There's a guide to try to understand which parameters are important to which type of processes. So that's, I would say, well established. Or in the beginning, when we started evaluating mixing, we generated enormous or huge tables, Excel tables with a lot of numbers, and we tried to match all the parameters, and we tried to understand why there were parameters that were different from one scale to the other, or from one reactor to the other. And we end up realizing that we didn't have to assess all of the parameters, and we only had to focus on what was important. Apart from the guide, as I said, which can be provided by the VisiMix support, apart from this guide, you learn from experience as well. So it's something that the more cases we have studied, the more knowledge we have gathered. So we more or less know what to evaluate and what are the parameters that we have to focus on.
Okay, well, thank you very, very, very much, Mark, for your presentation. I hope that everyone enjoyed the presentation and got good and useful information from it. Again, any questions that you still have that you would like to ask, I will put in the chat here. Let me just see. So let's see. Send to all. So let me put in info@visimix.com. And if anybody would like to ask additional questions, feel free to do that, and we'll do our best to get back to you. There will also be a recording of this session that we will send out in case any colleagues were not able to attend. Thank you again very, very much for attending our presentation. Thanks again, Mark, and have a wonderful rest of your day. Thank you, everyone.
Thanks to everyone.
Bye-bye.